Good. I'm Mike Lowe. I'm the head of the Department of Mechanical Engineering. And there's a picture not of me, but of something representing mechanical engineering here, I think. It's my pleasure to welcome you all here today. A very warm welcome to all of you. Thank you for coming. Especially warm welcome to Maria's family and friends who've come here in some numbers, which is lovely to see. And a warm welcome to former colleagues and friends who've come back, many of who were here in the past and are known very well. So it's lovely to see you back here this evening. I've got to say something about just a fire alarm warning before we start. We're not expecting a fire alarm. So if the fire alarm goes, it means it's real, or it's a real alarm anyway. And the briefing for that is that in the event of a fire alarm, follow the emergency exit signs to leave the lecture theatre, and the assembly point is on Exhibition Road. So the emergency signs are here and here. You can go out of either of these, and you make your way to Exhibition Road if the alarm goes, but we are not expecting it. Okay, so we'll start this evening's proceedings. I want to say a few notes of background and introduction before Maria speaks. The inaugural lecture is a high point for the department and the individual, of course. It's a time of celebration and congratulations. And we all know that the promotion to the level of professor marks an outstanding achievement for a research member of staff in the university. So being professor represents world leadership in the research subject area, as we will be seeing and enjoying the talk about Maria's achievements shortly. The college doesn't give these promotions away, as we know. It's a challenge, and it represents a very great achievement. So we celebrate, and we do this tradition very well, and I'm very pleased that this department has a good record of celebrating professorial promotion, inaugural lectures, very well. So this evening, we have I have the pleasure and we have the privilege to hear Maria, the inaugural lecture of Professor Maria Charalambides. She almost doesn't need any introduction because her picture seems to be everywhere. If you came in through the foyer, and you probably did, you'll have seen her picture on the screen. You'll have seen it on the publicity that was sent around about this event, and so on. So she's very well known. If you read the text on her picture on this screen on the way in, it says, "My research tackles problems that you would not associate with traditional mechanical engineering research." And then it mentions painted artwork, mechanical properties of food, and a number of other interesting things, a lot more interesting than the picture that's supposedly representing my interests here. I don't know what it is, actually. So food and artwork and things, it is interesting, and I can see some of you nodding at that. And I wonder if any of you have ever been invited to a meeting with Maria about chocolate. I had that pleasure last year, and I went along, and I'm sorry to say there wasn't any chocolate. So I missed the point about that. However, when she got going, the science of the subject is absolutely fascinating. And not just chocolate, but all the other many things you'll see that she does. And she's a world leader in this, and that's what we're here to celebrate. So I'd like to go back a little bit now, because Maria's been here a long time. So Maria started here as an undergraduate in 1985, and she did our undergraduate MEng program from 1985 and graduated in 1988. She stayed on after that and did her PhD, 1998 to 1992, and the PhD was on the subject of fracture mechanics applied to delamination of fiber-reinforced plastics. And her supervisor was former head of department here, Gordon Williams, and I'm delighted that Gordon is here, has come back here to be with us for the lecture this evening, so that's terrific. Gordon, welcome back. She stayed on after that as a postdoc until 1996, when she made an attempt to leave. She went to the National Physical Laboratory, where she was a senior research scientist from 1996. But in 1997, we got her back again, and she came back here to be a lecturer. She was promoted to senior lecturer in 2004, to reader in 2010, and now we're here to celebrate her promotion to professor. Currently, she's the head of the Soft Solids Research Group, which she founded. She's the head of the Mechanics of Materials Division in the department, and with that role is a member of the Department Management Committee. So she's very central in the running of the department as well as her own research. And I should add to that that she has been, over the years, a major and high-quality contributor of teaching to the department, significantly teaching the very important foundational subjects, first-year mathematics for a very long time, and first-year mechanics for a very long time that is still ongoing. So I'm very grateful to you for that as well, Maria. It's terrific. It's a fantastic contribution on all fronts. Maria's research includes material modeling and mechanical characterization of soft polymers and foods, micromechanics models of composites and cellular structures, experimental and numerical modeling of industrial food processes, such as rolling, extrusion, and cutting, the development of methods for material characterization of polymers, fracture and deformation in paint and adhesive coatings, amongst the range of things that she does. She's published over 100 papers. She has a wide range of funding from industry and research funding bodies. I'm going to say no more now, but just to welcome Maria up to give her lecture that we're very much looking forward to. Maria.
Okay, good evening, everyone. Thank you very much, Mike, for the very kind words, and thank you very much for everyone who's here this evening. It's a real honor to see so many of you here today celebrating with me my achievement. So this evening I'll talk to you about some of the work that was done in my group, the Soft Solids Group. And this is the outline of my talk. I'm a professor in mechanics of materials since 2018. So I'll start off by explaining what mechanics of materials is all about. Then I'll say what the challenges are in studying mechanics of soft solids, a little bit about me and how I got here, and here I will say how we use what we learn in this step to solve various real-life problems, and then I'll finish off with conclusions and messages. Okay, so I've taken these pictures from my first-year mechanics course, and mechanics, the question that it wants to answer is what are external loadings on structures that you want to study. Now, if the interest is how does this structure respond to these external loads, how does it damage, does it deform, does it fall apart, then that's in the realm of mechanics of materials. To answer this question, you need to look at the materials that make up that structure, and specifically, you need to know what the mechanical properties are of these materials. If you don't know them, then you need to go to the lab and do some tests to find out what these are. So let's say this is a green material that you want to characterize. You want to find out mechanical properties. First, you manufacture a perfect cylindrical sample like this one, and then you take it in a lab on a mechanical tester, and you apply a uniform load on this cross-sectional area, which is A, and you squash it, basically. So under the application of this load, you can calculate this quantity, which is called the stress. So this is the load divided by the cross-sectional area in which it acts. And this sample, it will deform to this new shape from its previous height h to the new height, the shorter and wider sample. The mechanical tester will give you the load as well as the change in the height or the deformation, and from the change in the height you can get the strain. So the strain is the change in the height over the original height. Now, basically what this is the response to the applied stress on this material. And for this test to be valid, the stress and strain have to be the same throughout your material. Okay, so what are the challenges with this type of work for soft solids? And soft solids could be examples. I'll give you some examples. It could be foods, it could be paints, gels, soft polymers, all sorts of rubbers, all sorts of soft solids which happen in many, many applications. So it's important to know what the mechanical properties are of these materials. So what are the challenges with these materials? So there's two areas where you have the challenges. One is in the experiments. For these materials, there's no test standards that will tell you how to make your samples, how to do the test, how to do your calculations to get these stress strain properties that I was talking about earlier. It's difficult to make samples of precise geometry, and sadly you cannot machine a chocolate sample into a cylindrical shape. It's difficult to grip or hold them because they're very soft without damaging them, so if you want to hold them to do a tensile test, for example, or a lot of them are so soft they're more in the complex fluid domain instead of a soft solid, and then they deform under their own weight. So this is before you start putting external loads on it. But even if you manage to overcome these difficulties, then you reach the next hurdle, which is the hurdle of how to find a material model that will fit this data that you're going to collect from these experiments. So we need a mathematical description that will provide the deformation as well as the fracture of the material that you managed to get data from for these experiments. So imagine here we have this stress strain curve and you test two materials. So this is one material and this is another one here. This material, its stress strain relationship is linear. It only goes up to small strains. This material is very nonlinear, and this could be happening right from the beginning. There's no initial linear slope. And it also goes to large strains. This material, when you load it and unload it, it will come back the same way, which literally means that at the end of the test, you have the sample looking exactly the same as it did before you tested it. Okay? There's no damage in this sample. This material, once you load it and then you unload it, it will come back a different way, and it will stop somewhere here, and no matter how long you wait, you have this permanent deformation in the sample. These permanent deformations are usually a result of very complex microstructures. A lot of these soft solids are natural polymers with complex microstructures, and that makes this behavior quite tricky to model. The other problem is that this material, when you're testing it, if you slightly change the temperature or the humidity or the speed that you're doing the test, you're not going to get very large differences, whereas this material here will show a huge effect. So this is all the things that makes modeling these materials very hard. These are some pictures from taken from some of our research papers. These are all mechanical tests that we've done. This is dough, tension of dough. This is compression of cheese, and this is gel, again, compression. And all of these are examples of mechanical tests. And this is slightly different. So we want to characterize this yellow piece of polymeric material here. And how we're doing this, we're putting it on a stationary surface, and then we have this spindle on the top, which will rotate. So you're basically twisting your material, so you're shearing the material. And these are called rheometric tests, as opposed to mechanical tests, the ones I showed you earlier. If your material is very soft, so we said, a lot of these materials are on the boundaries of solids and fluid, this could be your only option, of probing the mechanical response of the material. Okay, so this is just a summary of this introduction I've made for you. So first of all, you need to go to the lab and do lots of experiments under various different conditions. You amass your data. And then you need to examine the data to decide what mathematical model you'll need to describe this behavior. Once you've done that, then you need to use this data to calibrate the material models. Once you've calibrated your models, then you can use them to describe the deformation as well as progressive damage and fracture of your material. And this is all necessary groundwork that you need to do before you begin using this information to solve real-world problems. Okay, a little bit about myself before I show you these real-world problems. As Mike said, I got here in 1985 from Cyprus. This is a picture from Akamas. This is the opposite side of the island to where Agia Napa is, which many of you might have heard of. What people don't also know about Cyprus is that it has beautiful mountains. This picture was taken in the summer. We were there on New Year's, and this was covered by a meter of snow. So this is a picture of my school. This is my secondary school. It's the oldest school in the island. And I was lucky to go to this school because I had very inspirational teachers who knew the subjects extremely well. There's two more people that inspired me to be here. These are my parents, Nikos and Nedi. They're both engineers, civil and mining engineers. And for my generation, it was very rare for my friends, their mothers, to be educated to university level, let alone an engineer. So my mother was actually the first female civil engineer that was registered on the island. Okay, so I came here, I did my degree, I enjoyed that. I wanted to stay on and do further research. I did that under the supervision of Gordon. My project was quite interesting. It had both experiments and models. The experiments involved a lot of mechanical testing, which is the ones I've talked to you about. And this picture shows a mechanical tester, like Instron. This picture was taken last week. This picture was taken in late 80s, or beginning of 90s. There's some similarities in these pictures. The mechanical tester, the frame of it looks exactly the same, the double column with the load cell. There are some differences, though. There's a computer here. There's no computer over here. Instead, we have this gray panel, which had lots of multicolor push light-up buttons that you would need to press, a lot of switches and gauges, because the computer here drives the machine, whereas here we had to use this panel. The computer here also stores your data, whereas here we have this piece of paper here. You might not see it, and there's a pen there. And then this paper would roll on this table, and then the pen would get your trace. And this is how we used to get our data. There's another striking difference in these two pictures, and this is health and safety has moved a long way. There's no sign of a lab coat in this second picture. Okay, so coming back to my research. So I'll be telling you about some projects that we did that had to do with food. And all of those projects, the aim was the same. How do we build predictive models to determine how food will behave in whether it's an industrial process, manufacturing, or a human process? What happens when we eat the food? And we want to know that. We want to know what the impact of this process is on the food material and us, the consumer. So how we build this model is through, we use the material properties and the material models I was telling you in my introduction. And then we build the geometry of the process that we want to simulate and any loading, external loading boundary conditions. It's a good idea when you have models to always try and see if your results are correct, their predictions. So you'll do some experiments to validate some of the predictions. Once you're happy that this is the case, then you can use this tool to optimize your process in a much more cost-efficient manner than actually doing physical trials. This is an example of one of the manufacturing processes that we studied. This is rolling of dough. You can see what happens here. The dough is torn, and when that happens, this stops moving, and this is something that you really want to avoid on a large-scale industrial manufacturing line. If you have this simulation tool, then this tool will output the strain, the stretch that the material says in this direction as it gets rolled, and therefore you can predict before you do this that this material is going to tear, such that you can avoid it. You can use this tool to decide how to stop this happening, either by changing your recipe, your material, or you're changing your process parameters. Now moving to the oral process. This is what happens when we put food in our mouth. I'll only be talking about texture today. There's aroma and there's taste, which is not part of our research. Texture is basically how does food feel when it is eaten. The food industry wants to know how consumers will react to the new products. And how they do this, they have sensory trained panels like this. So these are individuals which have been trained, and they're asked to rate products on a scale from 0 to 10, say, after first calibrating what 0 means and what 10 means. What we're trying to do is to develop some tools which will help us understand how these decisions are made by the consumer. So this is the first project I'll show you. Here we wanted to see what the effect of the manufacturing processes, so extrusion and baking, is on these very popular crispy snacks. The extrusion is favored in industry as a manufacturing process because it's a continuous process. But baking here, so this is butter that you put in between hot plates. This tends to produce a lighter and crispy textures, and this is picked by consumer panels. They can pick up the differences between the two, and we have picked the differences between the two when we did our mechanical tests. So the question is, what is it that drives these differences? These are the structures of the two materials, and you can see the similarities in the two photographs. They're both cellular materials with thin cell walls. I should say that both products they have exactly the same density, so that's not what drives the differences. And the pore size distributions are also very similar. So to find out what the differences are, we take the three-dimensional images from X-ray tomography, and we use them inside these computer simulations to do virtual compression tests. What we do then is we get the output from these models, and then we see what value of mechanical properties do I have to put on this solid that makes the thin cell walls, such that the output of these models are the same as the experiment. And this gives us a measure for what the properties are of this solid cell wall, which otherwise would have been very difficult to measure. And we found that indeed this product, the extruded product, has much stiffer cell walls. The other thing we could do, of course, here is once we have the two geometries, is to input the same material properties for the solid wall, and then you pick up the differences. Again, this came out to be stiffer, and this is just the effect of the microstructure. So extrusion seems to lead to stiffer microstructures because of the different material in the cell wall, as well as the different architecture of the cellular material. The next project I'm going to talk to you about is there's a pet food industry wants to market these products here for cleaning dogs' teeth. Very difficult to brush dogs' teeth otherwise. We want these products to, when the dog chews these products, through friction, we want to remove the tartar and the plaque that builds up on the dog's teeth. However, dogs come in different breeds. They chew in a different way. Can we have a design tool that we can use cost efficiently to design these materials? And this is what we did to solve this problem. This is a skull of a dog. And we took concentrated in this region, which are the back teeth here. And we did two things. We used them to fit it inside a computational model, and also 3D printed these structures such that we could do a real test. And the idea is to try and see whether these two match. And they did. So these are showing the images at different stages of indentation from the teeth, increasing indentation as you go this way. And you can see that the fracture paths are modeled correctly. And the agreement was also very good quantitatively when we look at the deflection here and the loads that are measured in the machine at different speeds. Also, those did agree very well. The next project I'll talk to you about is this current ongoing project, which is how does microaeration affect chocolate and oral processing, human perception. Chocolate is a very complicated material. It has sugar and cocoa particles as well as milk powder, if you have a milk chocolate, and that's dispersed in a cocoa butter. And this is a picture on the SEM on a microscope that you can just about see maybe the crystals here. And what we've done here is we want to see what the effect of including aeration in the form of about 10, 15%. The scale of these bubbles is about the same as the size of the particles here. And we want to find out what the effect of this is. Now, these are so small that you cannot actually see them. And bubbly food and drink seems to be favored by the consumer. We want to understand why that's the case. And bearing in mind that if you don't see these bubbles here and you're eating this product and you actually prefer it to the one without the bubbles, you're actually consuming a lower energy density product as well. So what happens when during first bite, you have your material here and it's indented by the teeth, and the action of the chewing, the purpose of it is to break it down into smaller and smaller particles. So on this graph here, mechanical properties are very important to begin with. Of course, as this food goes into your mouth at 37 degrees, then heat transfer starts taking place. And Yanis here is helping us with this topic. And we're trying to answer questions like, does microaeration change this pattern? And then that has an effect on how quickly the material changes phase, for example. Does the consumer pick this up? Once these particles are formed, then they mix with saliva and they're squashed in surfaces in your mouth to form a bolus, that's what it's called, this soft solid. And then here you would do the rheological test to characterize it. Of course, this interaction with the tongue and the top of your mouth is also quite important, and maybe it does affect consumer perception as well. And this is in the realms of tribology, the study of friction. And here, Philippa and Mark are helping us to look at this problem. So it is a collaboration. This is a complex problem, and we're trying to, with different expertise, we're trying to bring it all together to understand what's going on when we have microaeration in chocolate. This is mechanical tests. On the left here is a 0 porosity chocolate, and here is 12 porosity chocolate. And you can see that this has started forming the cracks straight on. Actually, here the test has stopped because there was a crack that went right through the material, whereas this keeps on going. So it's obvious that the aeration seems to induce earlier fracture in the material. And this was evident when we looked at in vivo mastication tests. So this row is from chocolate that didn't have any bubbles, and this is aerated by 12%. And if you look at these pictures closely, from the first bite, you can see there's a lot more smaller particles here than there. So obviously, the microaeration seems to lead to higher fragmentation. What we're trying to do at the moment is to develop models that predicts these fracture paths, and that will help with understanding the aim that we had before. But also, it could be quite exciting, because if we have a model that predicts crack paths, then maybe we can strategically place sugar in those regions that will be exposed, and then you will actually sense them in your mouth, because at the moment we're eating a lot of sugar, fat, and salt that we don't actually taste it. So this could help to design products which could help us fight diseases like obesity and type 2 diabetes. Okay, moving on from after you eat the food, it goes down to your esophagus, and then it enters your stomach, where here you're going to get further disintegration, and the food will then leave the stomach to go to the small intestine, and this is where the area where all the nutrients are taken up from your food. It's important to study this because it affects metabolism and our health. And here we're looking for tools to design food structures such that they disintegrate in a controlled manner, and we benefit from the nutrients that are available in the product. One thing I've learned from mixing with lots of our collaborations in this subject, like the food scientists and the medical people, is that just because on a packet it says these are the nutrients that are available, it doesn't mean you access them. It doesn't mean that you will actually benefit from them. Whether you will or not, it will depend on how the food behaves in the gastrointestinal tract. So what actually happens to food in the GI tract? It gets mechanically loaded, so the walls of the stomach here will compress the material to break it down. It will hydrate when it interacts with the gastric fluids, and it also chemically degrades because of the enzymes. Here, I'm just going to show you the model which only takes this into account at the beginning. We're hoping to continue this work such that we can extend our models to include these too. Before I show you that, this is the material that we're testing. It's oatcake biscuits. We broke them into particles and mixed them with water at different contents to mimic the food that's in the stomach. And we did some independent tests in the lab. Basically, we had a cylinder, and we pushed it down, and we wanted to check whether the model, the lines, agreed with the experiment, just to make sure that our model is correct before we applied to the model of the digestion. So this is the stomach, and we don't model this exactly as it is. We simplified to this structure here. So we have an axis which is straight. If we do this, then this is called an axisymmetric problem, and it's good because you don't have to then model the whole lot. You just take a small segment. It's like taking a segment out of an orange to represent the whole orange. So this is our segment here, and these are the walls of the stomach that will undergo this peristaltic wave, and this is the food that will get pushed out here from, this is called the pylorus, into the small intestine. So this is the model. And you can see the peristaltic waves and how they break the food and push it out of the stomach. And using models like this, we can study a lot of quantities. One that I have plotted here is how quickly the food leaves the stomach. And of course, this is important nutritionist things that they might be linked with how quickly you're going to get hungry after you've eaten this meal, of course. Okay, leaving the world of food to something completely different now. The question in this project is how can we predict cracks in art heritage? This is one of 43 portraits that we're examining, and the interesting thing research-wise about these portraits is that there's 43 of them, and they're all stored in the same gallery, in Know House in Kent, and they're inside some gallery which has no modern heating. So by looking at meteorological data from 1600 to 2015, and using simple models, we actually found out what is the temperature and humidity fluctuations that these portraits have all been exposed to. Why we care about the temperature and humidity fluctuations, these paintings are made out of different layers of paint. When the humidity changes, each layer wants to expand by a different amount. It starts pulling on the other layers next to it, and that's how cracks form. Of course, this pulling is very small, but if it happens continuously over a very large number of years, then eventually you get fatigue, and this is what causes the cracks. So there's two types of cracks in such paintings. This is the interfacial or delamination cracks. Basically, this is paint flaking off, like you see here in the gilding of Charles III. So the gilding has come off and is exposed the original blue layer underneath. And the same here with Queen Elizabeth. You've got all this piece of the gilt, the gold bit that came off, and we have the black paint layer underneath. Here we have all the layers have come off, and you expose the wooden panel underneath. The second type of crack is a through thickness crack. So this is a crack that happens into the normal to the plane here. So you can see it here, King Henry VIII. So you can see these cracks are going through the layers, but also propagate along the painting. And you can see it here on the actual portrait, which is more severe, of course. And there's also some here as well. So these are the models that we built to try and predict how cracks will, when cracks will form as a consequence of this fluctuating humidity and temperature. This is the model that we use for delamination, the flaking off of the paint. This is a quarter of a paint, and this is the top view. So imagine your painting is this size. We're only modeling half of it. And in the middle here, we have a flaw. We have a crack. We subject this to the fluctuating humidity, and then we see how long it takes for the cracks to start propagating from this initial flaw. And this is the model that we use for through thickness cracks. So this is the cross section, and then the crack is going to go through the thickness, but also it can run along the painting as well. And these are some of our predictions. I have three scenarios here for relative humidity. This varies from 35 to 90 maximum, and this is what you would get on a calm day. And it would take just about 2 years for cracks to start growing. These two are much tighter controls that you would typically have. This is the V&A museum control. And you can see that as you make this more and more controlled, then it will take longer for cracks to start growing. And what we're doing at the moment is it's fine to find out when cracks will initiate. What's more important is how fast will these cracks grow, because it could be that they initiate, but then they don't grow very fast. If they grow very fast, that's a lot more serious, and that's what we're doing at the moment. Okay, this is a different project that we got involved with within the last year. It's part of a large project within 7 different departments of the college. The aim of the project is what can we do to reduce plastic pollution? So plastics are used in various industries. This chart shows you that packaging industry is the one that uses plastics most. And this graph shows the top 10 types of litter that were measured, that were quantified in Thames River cleanup in 2017. And you can see the biggest one is food wrappers. And the others are also plastics which are related to food and drink and fast-moving consumer goods. Now, this plastic pollution, there's been a lot of discussion about it in the media, which is held by very high-profile individuals like David Attenborough and Greta Thunberg here. It could be very dangerous for our environment or our ecosystem. We need to do something fast to reduce this. Okay, so what have we decided to do? We're going to look at these materials here, the multi-layer packaging materials that we all very aware of. We're all seen it very often in our kitchens. These materials have been very cleverly engineered, this packaging, such that it keeps the contents to as long a shelf life as possible, and therefore it minimizes food waste. They've also been engineered such that you use as little material as possible, so you save your material resources. And it could mean also that if you have a lighter package, then you will have lower transportation costs. This is the typical structure. We've got 5 layers here. So this is the outer layer where all the printing, for example, and the brand images will be printed on. The middle layer, C, is the layer that keeps light, moisture, and oxygen out. And this is the layer which is in contact with the food and also seals to form the pack. And the greens are the glue that sticks the other layers together. The trouble with this packaging is that once you've used it, it's single use. You cannot recycle it anymore. The reason is, provided that, of course, it doesn't just get littered, in which case it will directly go to pollute our environment. If it does get collected in waste management, it will get sorted into this pile of mixed plastics waste. And then what will happen to this, it will either end up in incineration or landfill. None of this is good. The worst thing is that you had a material, you spend a lot of energy, you did CO2 emissions to produce that material in the first instance, and then you lost it through this process here. Incineration, of course, will both of these will add to CO2 emissions, and we have also a risk that it could leak back into the environment. The reasons why these materials don't get recycled are summarized in this table. First one is sorting, which is not effective enough to pick up the different materials in your package. This is why it ends up in this mixed plastics waste. And anything flexible that's smaller than A4 currently does not get recycled, so food wrappers, for example. Even if you did recycle this and you tried to blend them to form a new material, that material is going to have very low value. The reasons are that its color is going to be a not so exciting dark green, grayish color. The mechanical properties will be very poor, which limits your applications. And that means that recycling is not economically beneficial, and this is why it doesn't get recycled. The last reason is the way that these packs were designed originally. Recycling was not taken in as a design variable. And the layers are very well bonded together, and it's unable to separate them. And if you could separate them, the recycling would have been a lot easier because you had a single polymer then. Okay, there's 2 types of recycling solutions, either mechanical recycling or chemical recycling. And in this large project that I talked about in the 7 departments, we're looking at both. Mechanical recycling breaks down the materials, but it does so mechanically through shredding, for example, and then you melt them all together to form a new material. Whereas chemical recycling uses highly reactive reactions to break down the materials to their precursors, the monomer that was originally used. And from here it's quite good because then you can start again and make whatever material you want. There's both advantages and disadvantages in both of these. This is very expensive. This is comparatively less expensive and is easier to integrate with recycling systems. But we're looking at both, as I said. This is looked at in chemical engineering. Here in mechanical engineering, we're concentrating on mechanical recycling. And within that project, there's two things that we thought that we could do to try and solve this problem. Here I have a picture from literature which shows what you get when you try and blend PET film together with a polypropylene film. So the PET separates out into these particles into a continuous polypropylene. The reason why this material is not very strong is because there's not very good adhesion between the two phases. What you can do is to add a small amount of chemicals, it's called a compatibilizer, which changes the adhesion of those two interfaces, and it makes, therefore, this material much better mechanical properties. So we're performing studies here, both experimental and modeling, to understand the effect of compatibilization on the recycled material properties. The second thing that we're doing is we're trying to look at layer separation strategies. So what if you didn't use those very strong adhesives? You could then separate the different individual films and make the multi-layer package. Or what if you didn't have perfect bonding throughout? You don't really need that. So then when you shred it, then you can separate the films very easily and recycle it in a much easier way. I'm going to tell you a little bit more about this. So this is a literature picture. Based on this image, you can make a virtual material, so with the same size distribution and volume fraction as the original. And then you can do mechanical tests, virtual mechanical tests, to understand what the mechanical properties are of this material as a function of the adhesion between the two polymers. We're in the process of actually doing our own, so we want to have used the literature experiments as well, so with collaboration with the aero department. This material, this kind of modeling is called micromechanical modeling, and this is something that we've done a lot of in my group. We looked at a number of materials under the microscope and tried to examine the effect of the microstructure on the mechanical properties. So a lot of materials, when you look at them with the naked eye, they look homogeneous. But then when you look at them under the microscope, you can see that they have a microstructure. So this is particles inside a continuous matrix. And then you can do the virtual tests to predict when this material will crack, how much they will deform. And you can use models like this to predict important mechanical properties like the fracture toughness here as a function of the amount, the volume fraction, the amount of the particles you have, and the size of the particles. Once you make these models and you're confident that they're accurate, then you can use them as very cost-efficient design tools to make new composite materials. So this is the end of my talk. So I'd like to end with my conclusions. I think the message I wanted to bring across today is that you can be seen to be doing lots of diverse things, but actually the underlying science is the same. It wasn't enough time to mention everything that we do in the soft solids group. We also looked at bird strike of airplanes with Tony and John. Sorry, no, with John and Iman. And we also looked at how we could develop adhesive patches to cure onychomycotic diseases on toenails together with Tony, Dries, and UCL. A lot of these problems, a single team cannot solve them by itself. So if you look at the problem of pollution, plastic pollution, then you need engineers, you need chemists, you need social science, you need people who understand about economics and business models, and you need people that know about the environmental policies. If you want to design foods that can lead to more healthier products for the consumer, then you will need engineers, you will need food scientists, you need medical people, you need nutritionists. However, if you have these big teams, then you can solve problems which will have a very large impact on society. Okay, so next I'd like to thank some people. First of all the people that did their research in my group, so the PhD students and the postdocs. I didn't have a chance to showcase everyone's work here today. But I'm very grateful for all your work. Every single one of you has made something which progressed the know-how, and this is why we are at the state of where we are at the moment with the Soft Solids Group. I would also like to thank my collaborators in mechanical engineering, the ones outside my department, but within Imperial, outside Imperial, the people who funded my work, funding bodies and industry, all the administrators and technical staff of the department and the college, but a special thanks to Val and Ruth. And also particularly for this evening, I'd like to thank Katie Livingstone. She did an amazing organization of this event, and James Romero, who pretty much wrote the abstract that you saw for me. Okay, so I also like to thank some very special people. So this is Ross, Nicholas, and Melina. Thank you very much, guys, for your love, support, and constant encouragement. Without you, I wouldn't have been here today, no doubt. I'd also like to thank all my friends here in the UK and Cyprus, my family who are watching in Cyprus. And I'd like to dedicate this lecture to my dad. Thank you. So we have time for questions.
We do have some time for questions. Yeah. So, and I think we're going to have two people with microphones. I see them. So if you'd like to ask a question, please put your hand up. But please don't ask the question until you have the microphone, because we would like everybody to be able to hear the questions. And the lecture is being recorded as well. So who'd like to ask a question? Yeah. Got one microphone here.
That was brilliant.
Thank you, Melita. Thank you very much.
Do you think it might be possible?
She's family, by the way.
Do you think it might be possible in the future to design the first plastic that you make a product out of so that it has better fracture properties to make better microparticles for the reuse thing? I know the blends, I guess the mechanical properties depend very much on what you get when you fracture the plastic you're recycling. So can we do something to design a better plastic so that it fractures in the way you want to get a better microparticle?
Yes. So with all these particular composites, how it will fracture will depend on the two materials that are making the composite, but also the geometry, the particle size distribution, the dispersion. So yeah, that has an impact on mechanical properties. It's not just the adhesion between the two phases, but things like particle size distribution. It could be non-spherical, in this case they're spherical, but also all these things do have a play, and there could be a design variable that you can play with, such that you can make a better plastic.
Okay. Another question. Yeah, one at the back there. Thank you.
Hi, so I'm in 12, and I was just wondering, because I'm trying to choose between physics and chemistry to do at uni, and I was wondering what specifically made you choose this field to go into?
Sorry, I didn't hear your question. Is it possible to repeat it, please?
What made you choose this particular field to go into?
Okay. So when I was hired as a lecturer in '97, my task was to bring food research into the department. Gordon Williams employed me then. He was the head of department. So this is how I started working on foods. But because of my background, again, through Gordon and my postdoc years, through Gordon and Tony, I was already working on composite materials and synthetic polymers. And of course, once you have the knowledge, you can still use it. And this is how I ended up going on through all these different problems.
Okay. Anyone else? Yeah, another question here on this side.
All right. Very nice talk, Maria.
Thank you.
Fantastic range of research. I just want to ask you a question which is a little bit off-piece. So you mentioned you've done a lot of teaching as well, and I just wanted to ask you, based on your time here, how do you think your approach to teaching has changed here? I was actually one of Maria's personal tutees, so I just want to hear her perspective on that.
Okay. I have changed in the sense that, I don't write on the boards anymore, but the reason why I stopped writing on boards is because they got new boards I couldn't clean. And this is why I moved on to tablets where I could write, with a digital pen. I use things like Mentimeter and so on. But, and I'm sure all these virtual learning tools are very important, but I think the human is actually the single most important factor on whether somebody is a good teacher or not. You can enhance it with the virtual learning things, but the teacher, the talent that you have to teach, I think that's what makes a difference. I can still vividly remember some lessons I had when I was at school from a particular physics teacher, and he didn't have any digital needs then. So, yeah.
Mm-hmm. Good. Yeah, one more up there in the middle. Thank you.
Different countries have different approaches to recycling. Would you think it would be easier to design materials which are able to be recycled in any way? Or is it easier to design the policies to match existing materials?
I don't think you have to do both together. So, you need advances in materials engineering, but you also need the people that work with policy, because working just on materials, you could end up with something which is very, very difficult, whereas then policy makes a new rule, for example, do not use thermosetting adhesives. Then you do not have to worry about that. So the policy at least will make it easier for you to try and come up with a problem. And you definitely need everybody to try and solve this problem.
Building on those earlier questions, is there any standardization or efforts to standardize on packaging and so on, so we use perhaps only one or two types of polymers rather than a whole range?
There were even attempts to make just a package out of a single polymer. However, talking to our industrial contacts, they don't believe that a single polymer can do all these different functions. There is a big push, and the industry, all our industrial contacts are very keen to solve this problem. They want to do away with this single-use packaging. So they are trying very hard, but it's actually, take a multinational company, for example. It sells products here, it sells products in countries which are very humid and wet. It's very difficult to design packages that will actually not be single-use for the whole world under these different conditions. But they are trying very hard, and we're hoping to help them. Yeah.
Okay, there's one in the middle at the front here. Thank you.
Yes, just a question about your industrial collaborators. You've mentioned the sort of motivation from the packaging side.
Sorry, mention?
You mentioned their motivation from the packaging side,
yeah,
wanting various features in the packaging. I just wondered what the motivation was in the food side. Is there any pattern to what sort of things they request from you?
The food industry, apart from the food packaging, they want to understand how the oral processing. That's their main interest from the food, because that's what affects whether the consumer will buy it or not. That's what they really want to understand. Once they understand that, then they want help to find out how to make, that food. Yeah.
Okay. Right. Last question then, up on the left there.
Hi, Maria. Thank you very much for the talk and helping me with my own research even. I wanted to ask if you prefer teaching or research?
Actually, that's a very easy question because I do like both. I really enjoy teaching as well. It's difficult to balance them, of course, but sometimes it's nice to have something completely different. And with teaching, I think I've said this before to my colleagues, I never feel like I'm wasting any time. I'm teaching, I'm achieving something. the research, you could be going down the wrong path, you could be writing a paper that gets rejected, you write a grant that doesn't get accepted, and you have that frustration. With teaching, you never have that. So it's nice to have the two, and it helps. It helps to have an academic career.
Okay, so on that point, very nice point, we'll move on to the last part of this evening's procedures. I'm going to invite Dr. Ulrich Hansen to come up and give the vote of thanks.
Oh.
Yeah, so first, thanks to Maria and Mike for giving me this opportunity to help celebrate Maria. So I'm a colleague of Maria rather than, say, a research collaborator. But I know Maria for, it's coming up to 20 years now. Basically since we both were first joining as new lecturers at the department. Now, as Mike and Maria herself pointed out before, Maria was here before that time. She was doing both her undergraduate and postgraduate studies here. And my own experience is that that time is a good time for, should we say, a fun story. So I asked Ross if he could think of a fun story that I could bring up today. He declined. You can maybe guess why. In any case, I feel I have my story, because the reason I asked Ross was because he was a PhD student in this department at the same time as Maria, in the same research group, and right after that, they got married. So it makes me wonder what was going on in those research offices and what kind of research groups Tony and Gordon was running. Yeah. So with you pondering that a little bit, I'll go on to maybe the slightly more serious part of the vote of thanks, which is Maria has already demonstrated to you that her field was, well, it's hard, as the title says. It requires a lot of scientific rigor, and Maria should have credit for taking on something which is very challenging. I myself try to stay away from it as much as I can, or else send my students to Maria. She also demonstrated the width and the breadth of her area. So I knew Maria was going to do a good job of this, and then I would really have nothing to add to it. Where I figured she might need a little bit of assistance simply because she's a very modest person, was maybe to make it clear how unique this was, what she's done. So I would say, as she said, she started this area sort of, let's say, about 20 years ago. And it was very small fry at the time, this whole area of solid mechanics. And she has really taken it from over these 20 years to now be a world-leading group, where really if anybody in the world needs to do this at this point, Maria's group is the place to go. As you can also see, she has these AWE, she has Nestle, and many big companies now putting in the money in the research group. So again, credit to Maria for that. The other thing she didn't get to mention, for the same reasons, is that she's published more than 100 papers in this area. Her work was in the finals for a very prestigious Material Science Award. She has no less than 2 best IMG papers, and she is on a range of influential professional organizations. Now, all of this is just symptomatic of the now world-leading group she, of course, has made out of it. So she just deserves credit for having made that group, I think. Now, I would like to take a little bit of a change of tack here, because, as I said, I'm not so much Maria's research collaborator, I'm her colleague. So really, her contributions to the department beyond the research are quite important to me. Now, Mike has already pointed out, should we say, Maria's teaching contribution, her increasing role in the running of the department. So I don't really have anything to add to that, but I always felt Maria brought something special or else to the department, and it's a bit intangible, but I was trying to put some words on it in preparation for this so I could communicate for you what I thought was special. And I really think Maria has a lot of integrity, and she has a lot of sort of care for the people around her, whether that's students or staff. And I could give you some examples of that, but rather I want to maybe move to the last point where I will bring it up again, which is to look at the future. Because, of course, it's maybe tempting to say Maria's now a professor, She now has the influential role that Mike was within the department that Mike was pointing out. And you might say, well, she's reached it. This is the peak. She's done. She's done everything she could. She reached the high point. But of course, it's not true. It's the beginning of something new, a new phase, where really Maria, with, should you say, for example, the cloud of professorship, can probably impact her research area much more than she's been able to in the past. Also, she has that role in the department, very influential in the department, where again, she probably has more ability to have impact now than she ever had before. And again, there, I think it's very important that Maria's special qualities of integrity and caring for everybody, that they will play a very big role in that. And I'm sure she'll make a big success of that, and I'm looking forward to see the results. And I'll thank you for all the contributions you have already made, and for those maybe even more bigger contributions you will make now in the future with your new roles. So if you can all join me in applause.